Yay. Okay, everyone take a seat. We have some more chairs outside if you want to grab a chair. If you have a couple more, feel free to do a couple more. And Ben, can you go in the back? Ben? Okay, good. Awesome. So thank you guys all for coming. All right, thank you guys all for coming. Thank you guys all for coming out. I know it's a little bit of a tight space. We had a little change in plans last minute with the venue, but it all worked out. Oh, keep the slides, go back one, Ben. If you'd like to, you can follow us on our Instagram and our Twitter account here. You can find all the latest things we post. We have our photographer. We'll post all our pictures there. So if you want to get your picture, if you want to be on the picture, you can do that. If you want to tag us tonight, that's always appreciated. It helps to bring more people into the community. So you can take out your phones now and take a picture. Don't be shy. Take a picture, follow it. I know some people already follow it, but maybe some people don't already follow it. So you can follow it. Did everyone get it? Did everyone get it? Did everyone get it? Did everyone get it? Okay, there's still a couple more people. Also, I'll just say, like, before we're going to start doing these dinners beforehand, and you can talk to the speaker. So just keep an eye out for that on the Luma, and so if you want to just chat more and also get to know more people. It was a really fun dinner today and the last time, so keep an eye out for that. Okay, so everyone have that. So take a picture, tag us, tag something on social media tonight. Thank you. Actually do it. Okay, next slide. So DeSciNYC has probably, like, the 5,000 number is a little small. I think it's closer to 6,000 now, and people have come to one of our events. We've had founders, we have people from the science community, we have crypto people, we have random people, everyone in between. And we have, like, lots and lots of people, as you can see here. We've had Brian Johnson, we've had Michael Levin from Tufts, we've had Jean Herbert from Einstein on tissue replacement. So we do a lot of, like, cutting edge stuff. Ideally, like, 50% of the people you should like, and 50% of the people should think. For any speaker, I hope that 50% of the people really, really like them, and I hope that 50% of the people really, really hate them. I want decisive people and people that are doing edgy and controversial things. So that's sort of like what we aim to go for. A lot of people are upset with it, but whatever. All right, next slide. The next one is going to be on the science of dating. This is a really interesting one with Dan Krass. He ran a website and he scheduled almost 3,000 first dates between people. And I've seen the talk and he sent me the slides. It looks really good. If you want to RSVP now, you can do so here. It's a QR code. It's a really interesting talk around what makes people like each other and what he learned from it. He has, like, all these very interesting stats and insights into it. And I'm excited for it. I think it'll be a really interesting talk. So you can RSVP here. We're sort of taking a little hiatus for Christmas and New Year's, so we will return in January. All right, next slide. Oh, okay. This is out of order. Next slide. What is decentralized science? So, why did we start DeSciNYC, and what is DeSciNYC, and what is DeSci to begin with? So decentralized science is thinking about how to use the blockchain to improve science. So how many people here are, like, blockchain people? Like, you like the blockchain a lot, okay? And then we have the other half who is, like, the science people. And you've heard of DeFi, which is around, like, decentralized finance, which is about, like, opening up finance to people that were unbanked, or unbankable, and opening up and democratizing finance. And that's great and all, but the issue at the end of the day is that you're only sort of shifting tokens from one wallet to another, right? You're not actually, like, creating value. And what I'm really excited about decentralized science is, like, you're putting actual information on chain so that people can begin to do science and participate in trials, participate in clinical studies, and they can upload things that are working for them. Maybe they've seen an archive paper or a BioX archive paper that is really working well and they want to comment on it. Now this is a way for creating a university that's like on the blockchain that anyone can contribute to and that anyone is rewarded for. And this is very interesting. So right now we're in a world in which science is progressing so slowly, and nothing seems to be happening. And part of it, we'll see how AI can fix that. And decentralized science tries to gamify science and make it interesting for anyone to participate. Secondly, science is really inaccurate. People today think, quiet in the back. People today think that like science is like the gold standard for everything, and like peer review is like the best thing in the entire world. But this actually is not the case, right? Like the peer review suffers from a lot of things. People don't care. People aren't incentivized to do it in the right way. You see at a lot of top universities like Stanford. That like even the top people are lying in their papers, and people aren't keeping track of like where the data is coming from and the inaccuracies that exist. But if you put all that data on the blockchain, it enables it so that there's many eyes on it, many AI eyes on it, and allowing more accurate data. So I think this is probably one of the more important things. Then right now, science is a little bit too closed off, right? So like a lot of the things that are happening are allowing for like only people that are PhD students to participate, or like professors, but this is a very small group of people. It does not reflect the general population of the world. So decentralized science hopes to open that up. And then lastly, the cost structure. So science is expensive now, but it doesn't have to be. Like there are ways to make science cheaper, and decentralized science is about how to do that. So we wanted to take all these ideas in which DeSci sucks today and try and make them come on in, and try and make them into like a fun game thing that you can do. So we started this company called Stadium Science. You can go to the next slide. And our idea here is to make like science as engaging as like a sport, so that people want to participate in science. People have an incentive to participate in science, and you want to make science and research almost like addictive and almost like a game. So we have this concept of like a social network for scientists where people are contributing data into like a pool, and the way it works is we have like a bunch of players who are wearing an Oura ring, and the goal is to try and bet to see who's going to be the best sleeper each individual night. So you're trying to create like a marketplace for almost like horse racing, but instead of for horses, it's for people. And if you like squint your eyes a little bit on this, it's like a prediction market or a betting platform to incentivize people to live healthy. So you're setting up like an optimization where you're saying like, we want to bet on who's going to be the most healthy person. And if you are correct, and if you're correct, if you look at their BMI, their age, their blood work, what nootropics they're taking, anything like that, that's all available. And you can accurately predict who's going to be the most healthy. So you're coming up with a model, either a mental model or an AI model on what is working well, and then you guess correctly. You're going to be rewarded for guessing that correctly. So you're incentivizing people to upload their data and create these like large data sets that anyone can participate in, and then you're also creating a lot of people in the crowd to be able to like participate in this. So it's opening up science to people who are outside of it. Generally speaking. All right, next. Yeah. All right, next. Next. So you connect your like Oura ring to the site. And then you bet on people. You can go to the next slide. So it's almost like a game. And there's this interface where you see all the different participants who are here, and then you bet on if you think that they're going to be the top sleeper that night. And they list all the different interventions that they're currently working on, the drugs that they're currently taking. So we have people taking melatonin, we have people taking peptides, we have people using the sleep aid, we have people using a sleep mask, all sorts of things. And we're generating this like really interesting model for which we can like judge how healthy people are, and for which other people can judge how healthy people are. All right, next slide. Next slide. Oh. Okay, so that's that. Go back to the first slide with the Oura ring. So if you want to be one of the competitive sleepers, you can sign up for our beta test. So who here has an Oura ring? or a Ring user, or a Ring user, or a Ring user. Who has a health kit or like an Apple Watch or something like that? Okay, yeah. So if you have an Apple Watch or a Whoop or a whatever, and you want to be sort of in the beta trial for this, and you want to be an extrovert and allow people to see your sleep data and allow people to bet on it, scan the QR code. Cool, cool, cool. Yay! And I'll send you a message later. Maybe you just want to email friends with me, and then you can also sign this. Cool. All right. Wait, one more. Cool. All right. All right. Go forward a bunch. Go back. We're also partnering with this meme coin token called Water Bear. If you guys want to be part of the airdrop for this, you can get here. It's basically free tokens. It's very cool. It's a free airdrop. We'll get your wallet address, and you will get tokens, and that's all I can say. But yeah. And it's also partnered with Sci-Hub as well. They help to sponsor these events. Okay, next slide. Oh, wait, do you go back?
Which one?
Go back, forward or whatever.
This one?
The other one. I'll fix this next time. Forward. Okay. If you want to download the Stadium Science app, you can download it here. That's the Oura Ring thing. If you want to stalk my sleeping or the other people who are participating in it, we have a bunch of people here who are using it as well. So that's kind of exciting. You can see how well everyone's sleeping and copy trade what's working well for them. Sleep is one of the most important things actually for being healthy. So it's really important. So Android, iOS, cool. And then lastly, next slide. If you want to work with us on this, we're really looking for BD people, marketing people, and design people. You can scan this QR code as well. If you're looking for a job, you hate your job, I don't know, whatever, you should scan this. Cool. All right. I think we covered what is DeSci, what is Stadium Science, what is DeSciNYC. So without further ado, I am going to welcome Siraj. No, but I want to set your laptop up too.
Oh yeah.
I am going to welcome Siraj, and Siraj is, maybe you can give it to Ben and you guys can set up. Siraj is, Ben, go to the first slide just so people can tag us again on Instagram while you're setting that. And you can help Siraj set up the poster.
We have a quick question.
Oh, yeah, go ahead.
Have you done like a peer-reviewed design of that sleep study, or is it just kind of gamified?
It's not a peer-reviewed, it's a great question. So it's not a peer-reviewed study because we are going to allow other people, we're just going to do things for like melatonin and things that are relatively easy to test. And then the goal is to not do like an explicit study, but just to collect a lot of data from a lot of different people and hope that we get enough data that will cancel out the noise and to allow it. But we're not sure yet. Right now we're still just like gamifying it, and then we'll get to how the study will work in a little bit. If you have experience in that sort of thing, like we're very open to it, but it's very hard to conduct a study on this type of platform because people are wearing different types of devices. People have different efficacy rates of adhering to a protocol, but this is true for also a traditional trial as well, so like that's nothing different. So it's a different type of study that gives you different type of results, right? But that's part of the sort of, you just have to account for that level of variance when you're doing this type of study. Like maybe it's only for people that you trust and that are people in your circle or people that you know directly, and then you'll sort of copy that, but we're still figuring out the logistics of how to make this like clinically useful data collection, yeah, for sure. Yeah.
Do you plan to make a web app for Stadium?
Oh, it's a web app there. You can just go to stadium.science also and do that as well. Was there another question?
Well, I was just thinking, I'm not sure why it would need a formal study. I mean, already having this sort of data available for free and for people to do studies on it is already very valuable, I guess.
Yeah, exactly. I mean, long term, the goal here is to create like a clinical trial platform where people can deploy different novel molecules onto it, and then participants can opt to participate in that and then get rewarded with tokens for that novel molecule. So say someone develops some sort of new drug or they want to try metformin, an existing drug, they can like deploy that, and people that are sort of interested in that by themselves without having to go through the FDA or something can say like, oh, this sounds really cool, I've read a lot about this on Reddit, I want to be one of the early participants in that and get rewarded with tokens. they can do that for that. But yeah, we're still. Do you have experience with clinical trials or?
No, I'm not a
Oh.
researcher in that space. No.
Got it. Excellent. Any other questions? Do you have to?
How about we? I mean, he's got the slides.
Is it unlocked?
Yeah, it's good.
Oh, wait, cool.
How do you full screen it?
Oh, that's for the end, but just the slide. We'll start off with the slides. That's on a different.
Okay, is it a different URL?
Yeah.
Okay, I typed in.
Oh, that's right. So we have Siraj here, and Siraj is I knew you guys can come in. Come on. I've known Siraj for quite a long time. He hasn't known me though, but I started watching Siraj's videos on YouTube sort of during pandemic. He has a really popular YouTube on what is Bitcoin that he did very early. He had he has like a lot of popular videos on AI and like the word to vec and all that sort of space. And he's like he's a very prominent YouTube educator on AI and crypto subjects. He has over 750,000 subscribers on YouTube, a very big Twitter following, and he's very clear in his explanations. And also, he doesn't do stuff that's sort of normal, right? Like he's always pushing the edge. He has a company called Trader GPT and Wager GPT to enable just the average person to get access to the financial markets. At dinner, we were talking about one of his goals in life is to enable sort of anybody to write a PhD level research topic, and open that up to sort of anybody in the world. So I think he's like a really good speaker for DeSci. And without further ado, let's give Siraj a hand.
Thanks everybody. It's an honor to be here. It's a very crowded room. Again, it's an honor. I think everybody here is very early in this space. It's still very, very early. Raise your hand if you remember what AI was like in 2017. Yeah, we have gone really far. You can see, like, you guys are pioneers for even being here. So again, it is an honor for me to be here. This talk is about AI for science in 2025. And the key question that we want to answer is how do we accelerate the rate of scientific discovery 1,000x? We go to the next slide. If not, we can just, oh, perfect. So I'd like to start this off with an educational shitpost that I made last week on X. And I'm going to read it to you. OpenAI, for context, released O1 Pro. That's $200 a month. And in the first hour of them releasing O1 Pro, I opened up X and I saw a bunch of AI influencers and educators that I follow posting tweet threads about all the 10 things you could do with O1 Pro. And so, you know, you guys remember what it was like back then. No one was talking about it. And within an hour, everybody's talking about it. So I decided to basically troll science by posting this. And I said, I spent $200 on O1 Pro and casually asked it to solve physics. Unify general relativity and quantum mechanics, I said. No string theory, no loops. It gave me wild new math and testable predictions, like it was nothing. Full link. And I put the link out there for anybody to look at it. And this post went viral. We go to the next slide. Yeah. And what O1 Pro gave me was this. And I'll read out some of this for you guys. This grand theory of physics. Transplakian hyperalgebra is the first thing. What is that, you might ask? Well, it defines it at a transplakian hyperalgebra, or TPH, is an associative bigraded algebra. Of course, we all know what that is. Equipped with a higher category structure, duh. Okay, it's got axioms, it's got scaling, it's got a sheaf of hyperalgebra. Right, so what is this? Right, so we go to the next slide. So an actual physicist came in, NYU grad student, and he's like, I mean, no, it did a good impression of how someone would summarize their work if they had invented new math, and maybe it made new predictions, but it didn't actually do those things. And he wasn't the only one. A bunch of full-time physicists came in, and they're like laughing, ridiculing this. Elon Musk comes in to weigh in on the discussion. He's laughing too. But he comes and defends me. At some point, it will be real, though. Thank you, Elon. You can always count on Elon to be real. So, you know, did I believe that O1 Pro could actually solve physics? Absolutely not. But do I believe that it could possibly solve it? Maybe, yes. But this was like enlightening for a lot of people because, yes, I was kind of like trolling them and I was saying things like, sounds like someone missed their trans-Planckian hyperalgebra class. But really, like, I prompted it further. I used Claude to generate better prompts, and I was giving Claude what these guys had said. I was like, here's their exact criticisms. Make it better math. And I, as a prompt engineer, believe that there is a valid prompt for everything, right? If there's a will, there's a way. But it turns out that even after reprompting it 3 times with domain knowledge and giving it their criticisms, it generated something that was even worse than it generated at first. It was even more of a hallucination than it did at first. Now, I deal with hallucinations every single day in my life. We go to the next slide. So like this is a real problem. It's in sports betting. I've got Wager GPT. I've got a bunch of DGens who are paying $200 a month to get the best, hottest picks for teams. And it works, but there's hallucinations, you know, and if it doesn't work, I can blame the hallucinations, right? But you can't always blame the hallucinations, especially when it comes to financial data. And I have Trader GPT as well as a product with paying customers. You can't have an AI hallucinate returns for you, right? You either make the money or you don't. So hallucinations are popping up all over the place, but they cannot pop up in science. We don't want it to pop up in science. So who is doing this? Who is automating science with AI? Well, it turns out that this company, Sakana.ai, out of Tokyo, Japan, has built this AI scientist. And their goal is to automate the entire pipeline of science, starting with the idea and moving it to check all of the existing citations on the web. Does this idea exist? Let's give it a score. Let's create a template for an experiment. Let's run this code and test it out. Let's update the plan. Let's make this a recursive feedback loop. Let's then create the paper. Let's generate the paper. And now let's give it to an LLM to peer review. Michael was talking earlier about how peer review is broken. He is absolutely right. So this looks at its face value like a great idea. Sakana raised, what, 50 million? They've got Hard Maru from X, one of the OGs of AI. Elon has blessed it. You would think that they're going to solve it. It's called the AI scientist, for God's sake. It's an agent. You go to their GitHub. They have 300 plus stars. This thing has already published 12 papers. But how can we be sure that it's not hallucinating? Well, they're telling us that they're running on this LLM and they're experimenting, but that doesn't change the fact that I paid for O1 Pro and got mocked by every physicist on Earth for claiming to do science. What makes you think, Sakana AI, that you can do science? We go to the next slide. Look at this. 2024, this year, scientific article with insane AI-generated images somehow passes peer review. This is disgusting. This got into Frontiers of Medicine, right? This is one of the leading papers that everyone's like, peer review is the all be all end all. Your LLM is never gonna do it. Well, actually, this is relevant for the reason that it shows an example of AI slop and how peer review is bad, but it also shows how are we going to verify anything? Like we need actual verification. This is like, if we don't get this part right, then we're going to have these actual PhDs who work their whole lives to attain this knowledge. We're going to waste their time reviewing all this slop that we're sending at them. So I can't just say, okay guys, go out there and generate AI. That's actually not very responsible, right? We want to actually accelerate science. We don't just want to say that we did something for the sake of it. So we go to the next slide. Well, it turns out that this is not some kind of new idea. In their charter, OpenAI's charter, what are they even here to do? Our mission is to ensure that artificial general intelligence, AI systems that are generally smarter than humans, benefits all of humanity. All right, let's get past that PR talk. What do you specifically mean? If AGI is successfully created, this technology could help us elevate humanity, again, vague platitudes, by increasing abundance, a little bit more quantifiable, turbocharging the global economy, I guess you could quantify that, and aiding in the discovery of new scientific knowledge that changes the limits of possibility. OpenAI themselves marketed O1 Pro as a PhD in your pocket. And yet when someone goes out there and uses it as a PhD in your pocket, of course the actual PhDs are going to get pissed. So this should not be people can be very tribal. This is not an us versus them, PhDs versus not. We are all in this for science. Science doesn't care about your pronouns or anything, right? Science just exists. It's like mathematics. So if this is their mission, we're all aligned. We want to live in this fully automated luxury space utopia where we don't have to work and pay rent, right? We just live, we exist, we enjoy each other's companies. We can do that with AGI, but we have to actually get AGI to do the hard part, which is science, right? We can't just have this thing generating slop and embarrassing all of us all day. So we can go to the next slide. Can this is really the key question, can this even be automated? If Sakana can't do it, if Elon Musk is laughing at this, if anyone who tries is just going to be LLM hallucinations, how can you be sure without a human in the loop? Well, let's see. This is a scientific method, right? We know this. This has always existed. Observation is the first step. Can an AI automate this? Of course, we have self-driving cars, we have cameras, machines. We can automate observations. That's easy. Question, can we automate this? Absolutely, we can have an AI generate a bunch of random questions till the end of time. Hypothesis? Absolutely, we can have an AI generate 1 million of these hypotheses. Experiment. Now this is the crux of AI in science right here, experiment. How do we automate that? We don't have a lab, we don't have a wet lab, we don't have a physics facility, we don't have the Large Hadron Collider in Geneva. We can't be running particle physics experiments in our laptop. We can't be doing that. So how do we automate this? We go to the next slide. Science considers there to be 3 mediums to run experiments on. And it's called these 3 Latin terms. In vitro, which is in a lab, in vivo, in an organism, or in silico, in a computer. These are the mediums for science. And ideally, we can just have it in silico. We don't have to deal with these 2. And all AI scientists are aware of this. They want this to happen. And that brings us to the next slide, which is AlphaFold 3. This came out this year, which is built on, I think, 5 years of work from Google and DeepMind on trying to predict how a protein will fold. And if we are able to predict how a protein will fold, we can design drugs to help target these proteins and essentially cure a bunch of diseases. That's what it comes down to. The reason protein folding is important is because it helps us design drugs to cure diseases, potentially. Not potentially, it actually does that, but the potential is for us to be able to move so much of what existed in vitro to in silico. And that's what AlphaFold did. It moved so much of the experimentation that scientists would have to do in a wet lab by trying out different combinations of these proteins and seeing how they interact. It was able to simulate that. And it didn't need a quantum computer, by the way. I thought quantum computing would be necessary. Feynman himself said that in order to simulate quantum mechanics, we're going to need a quantum computer. Actually, the CEO of DeepMind, Demis Hassabis, said a few weeks ago that classical Turing machines are probably going to be enough. And he's talked to some of the smartest quantum scientists, and it's going to be enough. So this is actually very promising because it showed how much of the drug discovery process, which involves trying to test out all sorts of combinations of how proteins are going to fold, how they're going to interact with all of these targets, and it does that in silico. So this was a huge deal, and using this, Google was able to generate a database of 200 million proteins that they were able to generate the model for with AlphaFold, and it's already being used to treat a bunch of cancers. So this was a great example of a world-changing, cutting-edge example of moving science to a laptop, out of the lab, onto the laptop. But there was another. What's the next one? But before we get to the next one, let me just briefly, in 2 sentences, explain more about how AlphaFold 3 works. The way it works is...
Back a slide. Yeah.
No, this was the perfect slide.
Oh.
Okay.
Yeah, just high level. There's 3 parts here. The first step is input preparation. every variation of AlphaFold, they added in more data because that is a part of the scaling law. One of the two scaling laws that we're going to talk about, which is the more data and more compute you give these neural networks, which are also called universal function approximators because they can approximate any given function if given the right parameters through backpropagation. In this input process, they was given even more data than AlphaFold 1 and 2, in that it's not just able to predict protein for humans, but for any living organism. And all the interactions of a variety of molecules, not just proteins actually, ligands, a bunch of different ones. So it's just basically, it's trying to be a general purpose LLM for biology. And it took Google scale resources to do this. And what we know about deep learning is that it is the cutting edge tool for representation learning, being able to find the features and important connections in this data set. But the part that made AlphaFold 3 unique from AlphaFold 1 and 2 was this diffusion model. And who here has heard of stable diffusion? Raise your hand. Diffusion in the past few years, great, I'd love to see that. In the past few years has really shown people the power of generative modeling for images. But it's also useful for biology. It turned out to be very useful for generating a bunch of random noise from these set of proteins and then iteratively denoising those proteins to try to reconstruct them. And this allowed the machine to, over time, learn how to construct novel proteins that it had never seen before and predict how they would interact. We go to the next slide. So Google's got its whole domain, it's got its team focused on biology. They're good. But we want to, as individuals, without a lot of resources, who just want to do science, we want to do something that we can actually do that's accessible to us. So here is this donut of knowledge I found from Reddit. And it shows very roughly all the different sciences and I guess art forms that we could be using AI for. And unfortunately, a lot of these require, remember those two concepts, in vivo or in vitro, whether it's chemistry, human biology, medicine, all of these are going to require some physical equipment. Now, the one that's obviously not going to require that is computer science, but we're not going to focus on computer science. But if you notice here, there's one branch of science that is very close to computer science, and that's one of the formal sciences, and that's mathematics. So that's really interesting. Mathematics is interesting because it's not quite computer science. It's in a way it's a superset of computer science, but in a way it's different from computer science. So what if we built an AI that could make new discoveries in math? Then it wouldn't need a wet lab, ideally. It would just need a computer. We go to the next slide. Well, damn it, Google already did that too. And they did that this year. And it's called Alpha Geometry. And it is an Olympiad level AI system for geometry. And once again, they took this idea of science and they moved it completely in silico. And what Alpha Geometry did is it outcompeted all but the gold medalists in the Olympiad. And it was able to solve proofs for a subset of math, geometry. And it didn't create new math, but it was able to solve proofs better than almost all of the other participants. And this is really amazing. People didn't think that an AI could do this, that it could solve proofs at a level of a human at this stage of thought. Next slide. And before we go on further, I just want to take a second to just go over our first proof with you here, just so we're all on the same page of like what a proof actually is in this specific scenario. So we're going to have a theorem. This is our theorem. We're scientists here. We're going to propose this today. We're going to declare that for all integers n, if n is even, then n squared is even. So I'll say that again. If n is even, so if n is 2, then the square of n is also going to be even. So the square of 2, 4, that's also going to be even. If n is 10, that's an even number. The square of n is going to be 100. That's also going to be even. That's the theorem that we're making. So in Python code, we could just create a function that says, you know, take this input n and then square it, and if the square is even, return true. Something very simple in 3 lines. We could do that, but that doesn't prove it. It just shows for one case. In order to prove it, we're going to need to write out a deduction. And this is how we do it. We're going to pick an arbitrary even integer n. We're just, whatever it is, it's an even integer, we're going to call it n. And we need to show that n squared is even. How are we going to do that? Well, we can logically deduce that since n is even, there's some other integer, we're going to call it k, such that n equals 2k. So if n equals 2k, that means that n squared equals 2k squared. Well, 2k squared is the same as 4k squared. Well, hey, 4k squared is the same as 2 times 2k squared. So from this, we see that there is an integer m, namely 2k squared, where n squared equals 2m. Therefore, n squared is even, which is what we wanted to show. Now, we did this through a series of algebraic relations. These are operators that are logically sound, that don't care what you believe, they just exist. And there's a set of these, and we can construct a database of these, and we can call this a deductive database. I just want to show you guys one more proof really quickly, and that is this proof. You don't have to understand everything about it, but I want you to understand the general idea, and that is we propose a concept of theorem. In this case, it's going to be cosecant squared of x equals 1 plus the cotangent squared of x. That's what we want to prove. Well, to start, we're going to perform this operation on both sides. We're going to divide both sides by sine squared, and then we're going to factor it so it looks different. And then we know these two facts already exist outside of this equation. And because these two facts exist outside of this equation, this is true, and we can prove the initial theorem. So essentially, making a proof is making a set of logical statements that successively deduct that the original theorem is true. I think I just went into a recursion there, but hopefully I give you some idea of a proof. All right, let's move on. So, like I said, there's a ton of databases out there. We've got a real-time database, centralized database, parallel databases, distributed databases. But what alpha geometry used is a deductive database that we talked about here. And they store in this database all of these relational algebraic operators that exist. And these are just they're mathematical facts. And by combining them like Lego blocks, we can prove anything to be true. And that's actually really useful, that idea that we can mathematically prove something to be true when it comes to hallucinations. We go to the next slide. So the idea for alpha geometry was to take a proof, let ABC be any triangle with AB equals AC. Prove that the angle ABC equals the angle BCA. And they would deduce this through a series of algebraic operators that the LLM, the neural network, would generate. And it would try out different combinations of these algebraic relations through trial and error. And it was essentially a search. It's essentially a search problem. And mathematicians will tell you the same thing. When they're trying to think of a new idea, they are searching through the space of potential ideas. Sometimes it comes from their subconscious. You don't know where it comes from, but it comes from search. And this was one search strategy that was somewhat effective, but it didn't quite beat the gold medalist, so it wasn't that effective. But this idea of using a neural network to come up with logical rules that it then tests through reinforcement learning, trial and error, to come up with a theorem that is provable, that's actually very useful to this idea of AI for science. We go to the next slide. And one more thing about alpha geometry, the way it was able to learn all this is through self-play, which this AlphaZero was one of their earlier AIs that was able to learn through self-play the game of Go. And it was built off of AlphaGo. And they learned that self-play, synthetic data generation, is actually much more useful than watching humans play. Self-play is one of the best papers in AI. George Hotz, who runs comma.ai, he personally told me this was his favorite paper. I never forgot that. I think this is a very beautiful idea because it shows when a lot of people talk about the data wall, or like we've hit a wall in AI. If you look at Ilya Sutskever at the NeurIPS conversation last week, we haven't hit a wall. It's all about synthetic data generation. The top minds in AI know this. The results show this. So at the end of the day, self-play is the key. And self-play can be thought of in a lot of different ways. You could think of it as prompting your frontier model to create a bunch of synthetic data sets. That's one way. But reinforcement learning is like the OG way of doing it. And that is what alpha geometry did. It learned through a deductive database, trying out a bunch of proofs, and then coming up with the optimal solution. Next slide. But, DeepMind's worked on geometry, but what hasn't been worked on? I want to start with number theory, because number theory It's completely in silico. You don't need a lab. You can actually make a novel discovery, and you can prove it with this technology that I'm talking about, that I'm about to reveal in the next slide. But number theory is really cool because it describes all the numbers in the world and the relations between them. Next slide. We see this all over the place. You know, it's in the golden ratio, the Fibonacci sequence. This was a beautiful number theory problem from the International Math Olympiad. Find all integers mn such that m squared plus 1232 equals 3 to the n. Ramanujan was a famous Indian computer scientist. He was quoted as saying, an equation means nothing to me unless it expresses the thought of God. I thought that was a cool quote to add. He was a number theorist. Number theory is very cool. You know, it's not just because it's the only thing we can do with AI right now that's fully automated. It is, but it's also because it's very cool. So, next slide, please. So, we want to make an AI that will generate novel math that works, legit math. Something that any scientist will look at and say, yep, this is legit, and an AI did the entire thing. It came up with the idea, it came up with a hypothesis, it experimented on the machine, it verified those results with mathematics in a logically sound, structured, rock-solid way, and it used AI to peer review itself through a series of agents, of peer review agents. But how do we, and we know about all those parts, but really the hardest part here is the experimentation part. And so we want an AI that's going to be able to generate proofs for everything that it generates. And there's 3 programming languages currently for generating proofs. Isabelle is one, not enough libraries, I would say. Coq is the other one, and Lean is the one that I want to use. It was actually created by Microsoft, and it's used by the Ethereum community to secure smart contracts. There's a huge history of automated theorem proving, which is what this subfield is called, in Ethereum, in blockchain. If you guys have heard of ZK snarks, ZK proofs, all that stuff uses mathematical verifiability. It's using these algebraic operators that I'm talking about, just not for AI. All right, next slide, please. So I want to choose Lean for this, and I'm just going to show one quick example of Lean, just so you guys get a little flavor of what it feels like. So let's say we want to write out the statement x equals the absolute value of x. I'll say it again, x equals the absolute value of x. And that's really simple to write out in Python. Definition, absolute value, input parameter x, return the absolute value of x. But it only works for some numbers. We can test out a bunch of numbers, but how do we know that it's going to work for all possible numbers? Well, in Lean, we can write out the same thing, but instead of saying def, we say theorem. And we name our theorem what we want to call it. We're going to call it abs non-neg, for absolute value non-negative. And then we're going to define a number x out of all real numbers, z. And so it's using these algebraic operators to say it's going to be equal to the absolute value of x. And built into this language is a mathematical operator that will deduce the statement that I said using a series of algebraic operators. If anyone wants to know if this is true, it's going to output that proof. It's going to output the proof. And so this idea of the system outputting a proof, I want us to get really familiar with and really like, because we're going to need that. Next slide, please. And why will we need that? Well, Toyota had an unintended acceleration that has killed 89 people. That was the headline. Nike Capital says that training glitch cost $444 million. Who here has seen a broken 404 page by raising hands? Every single person. The reason this is happening, in 2020, CISC estimated that software failures cost the economy $1.56 trillion. The reason this is happening is because most software that we ship is not mathematically verified. And why would it be? We don't have time to sit here and learn about proofs and trans-algebraic geometry. And we just want to build stuff that works and profit and help people. But unfortunately, it's causing a lot of unintended consequences that can result in death. So this is actually really important because hallucinations are killing people. So to solve hallucinations, we need to use math. And we need to use provable math that is going to show that our AI isn't hallucinating. We need to show it. We can't just say it. We have to show it with math. So next slide, please. So this this area of using AI in theorem proving. It's called automated theorem proving. It's been around for a couple decades, but like all of AI, not really much progress has been made until the past 5 years. Alpha geometry was the best paper in this space, and the idea is that it's just going to come up with a bunch of tactics. It's going to create a tree of possibilities through brute force, trial and error. Does it work? And that's all we need to do, is we need to get an AI to come up with the right proof for whatever it's trying to propose or generate. Next slide. And why has this not been done? Well, it's prohibitively difficult because a lot of math is not in computers. It's just still in papers. It's literally still in like paper form. Tons of theorems from the 1700s and 1800s. It can take a lot of work. Now with Claude, we can just run Claude computer usage and just vision mode and just take that 11-person years of work and turn it into an agent. But it's virtually all software that ships today is unverified, and this is actually really exciting, by the way, because a lot of us, including myself, thought like the fun in AI came from the complexity of all the papers, and like it was so fun to look at all the techniques, and now it's just like, transformer, some reinforcement learning thrown in there. But this really allows a whole new possibility of like, if you're a smart, motivated person and you want to do something in AI that isn't very saturated, this is a great area to focus on, because downstream of this is science and basically the end of hallucinations. Next slide. So yeah, this just kind of further reinforces the idea of you have a transformer, it generates a bunch of tactics, which are algebraic relations, and it just combines them like Lego blocks until it finds the right combination that's going to work, and it returns that. Next slide. And there's been a lot of talk about this new scaling law, which is inference time scaling. We've had the pre-training scaling laws, GPT 1, 2, 3, 4. We all know about that. More data, more compute makes the model smarter across a whole bunch of evaluations. But with O1, we saw inference time compute arise, and that shows that the longer we let a model think when we prompt it, the higher the likelihood that the output is going to be aligned with the evaluation that we're running it for. I actually think that there's a third scaling law that we're not talking about, and that is a law involving these algebraic relations that I'm talking about, automated theorem proving. It doesn't matter how long O1 thinks. It's still going to output bullshit if we say generate novel physics. The only way it's not going to do that is if it's thinking and reasoning using these algebraic operators and mathematical theorem proving programming language that I'm talking about. That's the only way that it doesn't matter how smart you are, show me the math at the end of the day. And so let's not just, I just want to put this slide out there to say that let's not just think because O1 is reasoning that we've solved reasoning. Actually, reasoning is just getting started, and so much of reasoning doesn't have to do with text-based autoregressive models. It has to do with math and reasoning through math logically and deductively. Next slide. And so, I wanted to build this, so I built a little proof of concept that's going to automate the entire pipeline for this, and it's an open source project, and it's free, and everyone can use it, and we're going to give it, it's called Science Flow, and it's live on the web too, and it wasn't really that hard to build. Anyone can build it. Essentially, I asked GPT-4 to generate lean proofs, specifically. So fortunately, GPT-4 was trained on lean as a programming language, so I don't just ask it to generate anything. I say, make a proof in lean and then verify it in lean. And that way, it can actually, you can verify that the science it's saying is real. So I want to give it this famous, unproven number theory conjecture, the Collatz conjecture. And it's a famous unsolved problem in mathematics, but it's actually really simple to state. All it states is that for even numbers, divide by 2. For odd numbers, multiply by 3 and add 1. And if you do that enough times, all positive integers will converge to 1. That seems true. People have tried out up to hundreds of thousands of numbers, and it works for all of them, this conjecture. But they haven't proved it yet, because the proof is too complicated. and nobody's been able to do it. But let's ask AI to do it and see if it can do it live today. This is the last slide. You don't have to go to the next slide. I'm just going to go back there and enter in a prompt, and then I'll come back here. So before you guys clap, let me just go back there.
While he's doing that, you guys all smile. And all right, 3, 2, 1, smile, smile. One more. All right, actually smile this time. Smile. There we go. All right, this is now we can do the prompt.
Okay. Okay. Yeah, okay. So I just asked it the prompt, what happens if we modify the collab sequence? And, okay, so it just did it. So I asked it to do new math, solve this problem, and it just did it. So here's the lean. It generates a hypothesis. It automates the discovery process. It validates the proof in the lean compiler, so we don't have to just take its word. And then it generates the paper that you can then download. So this is the full scientific pipeline automated for the only science that is completely in silico right now, and that is number theory. Idea generation, pattern analysis, automated discovery, proof validation, paper generation, publication. You can submit it to archive, but that's after it's been verified. If you could scroll down to the bottom, that would be awesome. Keep going, and stop. And then it verifies no automated empirical verification was performed because the hypothesis could not be parsed. That's actually a great thing. That is the AI saying that it was some bullshit. That was a hallucination. I couldn't compile it. But it's so, and look, the peer review even, it said, your proposal to modify the collapse conjecture by changing the function applied to odd numbers is intriguing. This guy says it's intriguing even though it doesn't work. So even the peer review is hallucinating right now. It's also because it's GPT 3.5 Turbo, it's not the latest model, and that was just for testing. But at the end of the day, all parts of this could be hallucinating, but the verification will never hallucinate, because math never lies. So I just want to leave you with that. Math never lies. Automated theorem proving is awesome. I hope you guys learn more about it. The future of AI and science is really cool. If you want to follow, if you're interested in this, follow me on X. I'm going hard on X this year mostly, and then YouTube secondary. And then of course DeSci, shout out to Michael, love this community. Thank you guys.
Who has a question?
With doing the formal verification as a test case, does it like iterate through every real number on the simpler level?
It's not a fuzzer, right?
I don't think it does.
Okay.
No, this was like a very bare bones like.
Does it take a long time to compute though?
Yeah, it does. Actually, that's
Okay.
why I had to use GPT 3.5 Turbo because it times out on Heroku, which is it takes like 120 seconds for inference. So I had to cut it down to 20 seconds. That's why it's a lot better if you make it.
Oh, I see.
Yeah.
So most of the time is Lean doing the formal verification, right?
Yeah.
Okay. I see.
Yeah. Yeah.
What did you mean like software is not verified, or how would you verify it?
For any code base you have, it's like writing unit tests, like test cases for it. It's like a reflective language that's on the side. It's kind of like CUDA optimization. It's almost like GPU optimization. Like you can have a for loop in Python, but in CUDA, you can optimize the specifics of it, like where it's running, on what chip, what parts of the chip. Similarly, for like software, if I have a loop running, I can write a lean script that's going to formally verify that it does what it says it's going to do for all cases. Python will only ever show like some cases, well, any programming language will only show some cases, but formal theorem proving languages will show that something works for all cases. And that's really the key difference, all versus some. It's hard to understand. I'm still learning it myself, but yeah. Yes.
We heard about the test-centered development or test-based development.
Yes.
It's like a lot of like Bonnie frameworks that develop this for different levels of software.
Yeah. No, I
It's
don't.
not mathematically based on mathematics. It's based on how we structure code to be able to test it. Because if you brute force it, it's too much. It's like a combinatorial explosion.
Yeah.
Unit tests aren't a full formal verification of a program though. It's just like some arbitrary thing that you're testing, right? That's TDD, like testing group development, is often for like unit tests, integration tests, like these different things, but like an automated theorem prover can prove with mathematical correctness, like some assertion. It's different.
Yeah. Well said. An assertion. Yeah, that's a good word for it. Yeah.
Is this the same as symbolic verification?
That's a good question. I would think symbolic verification, this is included, but there's more to symbolic verification. Like, this is like, yes, it's verifying symbols, which are like algebraic symbols, but I think symbolic verification could also include like all sorts of other cryptography and like terms that are not like necessarily automated theorem proving. Yes.
It's like a proof library. So like once you run this once, like okay, when I run it, it runs in like a second. It's a very happy proof.
Yeah, and that's a great comment, and I forgot to mention that. Yes, there is a proof library, and once you use it once, it's reusable forever. It's like a library of truth, like an actual library of truth. And we can build that. That's actually really exciting. Yes.
Is verified code also similar to debugging and also testing UI, UX? So might run in one like browser and then crash in another one, give you, or different
interesting.
devices.
Yeah, it could if they're both using the dependency for like Lean, if they're both trying to verify a client side, but ideally that's not the case because of the way the system's set up. I have had that issue on Heroku where like the compiler wasn't working and I had to install it, so yeah, I still see there being some dependency issues, yeah, even if this is like, you gotta make sure the dependencies are there. Yes.
I know the main point of the program was just, I guess, verify scientific work, but I guess how do you see yourself, or do you think it's possible integrating into your own programs that you built, just verifying things that, I guess, go through AI and people have questions about, but, because even when you prompt it to do things, there's all these hallucinations that happen on, regular, I guess, day-to-day use of a program like ChatGPT.
Yeah, like anything like mission critical I'd want to use this for. Like if I was working on med tech, devices, medical devices use this as well. Like you want to make sure that a device doesn't return a -1. And like you can write a Python script, but like if it does, someone's pacemaker could die. If you're like secure tunneling into a pacemaker, you've got like an API for that. It can never return -1 or else the thing turns off. So like you want to mathematically verify for that for all cases, it'll never return -1. But like if I'm just writing like a script for some sales AI tool, it probably won't need it there. Yeah. Yes.
Hey Siraj, thanks for coming, great talk. Just to clarify, are you proposing that automated theorem proving should be used across many domains, or this is an example of one approach in one domain?
I'm saying that this should be used in many domains to help solve the hallucination. It's one part to help solve the hallucination problem. And people are already thinking about this, but just like putting more light onto it, try to shed more light onto it. Like this is a really useful area of AI research. And cryptography, it's like an intersection, right? Yes.
The verification is done by another LLM, or is it?
It's different instances of the same LLM, and they're all prompted to be different. It's all GPT-4 or GPT 3.5.
I think there is probably a theorem which says that LLM or any LLM cannot determine if the other LLM has hallucinated. I think that there is a famous theorem in computer science that a program cannot tell whether it will ever finish in a finite time. So I think it's inherently incompatible that it doesn't know that it's hallucinating. So I feel like there is incompatibility between mathematics and LLMs?
Yeah, it's like if the compiler's output is true or false, then it could say it, but yeah, it could still hallucinate if it's hallucinating the output of the compiler. Yeah, so I guess that's still like an issue. You would need to think about that. Yeah.
What was your inspiration for asking it to modify the Collatz conjecture? What did you find to just ask it directly to prove the original Collatz conjecture?
I asked ChatGPT for the optimal prompt for it that would make it most likely. I always ask it this, like, give me a scalar value for the highest likelihood that this is going to do the task that I want. And then it gives me like top three, like this prompt is 98% chance going to come up with a novel scientific discovery. Give it your system, and I gave it the code base. Yes?
Would you be concerned that all of this sort of value would accrete to the big players in the space if inherently you would reach some sort of a compute limit? Or would you consider some sort of, if you're looking to solve these big problems, like eventually you're going to hit a compute limit, irrespective of whether or not you're indexing against mathematically proved theorems to sort of substantiate your answer. But would you consider that to be a good use case to decentralize compute? I believe with Meridian prime numbers, they do something similar to that, where they decentralize compute, and you can actually offer up compute from your computer to help find the next Meridian prime.
I've always loved that idea. BitTensor, there's like any startup that's trying to decentralize compute, I'm always a fan of. It's very hard, obviously. I'm sure people are doing it well. Yes, is it related to this?
Yeah, we're doing something. I could talk about it.
Oh, perfect. Yeah. I think if it works, in that case where there's a working world where decentralized compute works, this would absolutely be amazing. I think this could tie into incentives as well, and ideally we just have people who are excited to do science, and there's a path for them to excel outside of academia, and incentives are like a huge part of that. So yeah, it's really cool. Yes.
I didn't understand, but what exactly is the hallucination problem?
Yeah, no, good question. Hallucinations are something I deal with every day. Basically, it's an AI that is going to output text that is not true. It's not grounded in physical base reality, and it's a huge problem.
So it's just making up an answer.
It's making up an answer.
Okay, I see.
Word salad.
Are you able to know more about details behind how that was created?
The AI for the
hallucinations.
hallucinations.
Can you speak in very technical detail? Like it's obviously drawing from real data set, but sometimes the inference, the tone, the syntax, the logic is something is missing.
Yeah.
In the translation, in the transmission. Are you able to speak to the technical level?
Yeah, I think it's a really good question. Like there was this project Deep Dream where it showed how an AI like Google had many years ago, where it was trained on a bunch of dog images, and then it was asked to generate other images, and it still showed dogs, and it was very trippy, and it basically showed how neural networks and dreaming are very similar in humans. Like this idea of we see things, but it's also it shows patterns of things we've already seen, and it concatenates everything together. Okay. And so hallucinations, I think, are like a waking dream of a language model, where it's it thinks that it's making the right connections between the weights of the network, but it's not in the right context. It's essentially dreaming.
But it's tied to prompts though, because I think they definitely done studies where it's you can ask the same intended question, but if you phrase it certain ways, you'll get different responses.
Yeah. Yeah, this is probably the biggest problem in AI today, the number one thing, hallucinations. And yeah, I think this is probably the best way to solve them. Just mathematically verify the outputs of your AI before it gives it to you. So if ideally the AI does it before it even shows it to you. It's here's what I have to say. It's how can you be sure? Let me show you the proof. And here's the proof, and then here's all the citations, and that's where we want to get to ideally. Yes?
I think this sort of, you, I believe, articulated 2 or 3 levers in terms of
improving the reliability of LLM outputs, one of which is pre-training, the next would be test time computer, inference compute. But I'm sort of thinking now too, like the controls that we clearly don't have on academic research papers that are getting published with like preposterous images, and I've even heard of other situations where people sort of in a trolling type way submitted and were accepted to prestigious publications. Like it really just does seem like if that is sort of the ground source of truth for a lot of like the training corpus incorporated in these models, like that's such a big problem that we're going to need to solve in order to just boost data quality. Sort of going in, I feel like the decentralized approach might be the right way to do that.
Absolutely, that's a great point. Like all these models are hallucinating, and they're hallucinating similar answers too. Like the word delve. I'm not sure if you're, delve. All these models are saying delve. And why is that? Why are all these models hallucinating the same way? Well, there's two possible explanations for that. The first one is that after GPT 3.5, every single language model was trained on synthetic data generated by the GPT family. So they're all just training off of GPT synthetic data. That's one explanation. But a more interesting explanation, I think, is called the Platonic ideal hypothesis. And it was a paper that just came out at MIT 2 weeks ago, I saw on X, where it said that all LLMs converge on the same shared understanding of a statistical reality because there exists an ideal statistical reality. And Plato suggested that back in the day, that there's this ideal reality, and all LLMs are converging to it. So that's one interesting one, but it's unclear. Like, is it the data or is it? Yes.
I thought like on somewhere I read, it's like the people who like label data for GPT, and they sort like they tend to come from like one region, so they tend to use the same like language traits, right? Like they they use like delve a lot. I remember somewhere around.
Ah, I could see that delve all over the place.
Yeah.
Or certainly. I remember Claude always starts out with certainly. Needs to stop doing that. Yes.
Do you think that like the fundamental issue of hallucination can be like resolved, or is it something that's going to just kind of always be around in AI and can only be like circumvented through things like verification?
I think hallucinations are like going to be solved, but they're always going to be at that base layer. Like the only way we're going to solve them is through math. We're not going to solve it through more text for pre-training.
For us to understand, hallucinations come from using neural networks. And if that proof system that you just outlined here does not use neural networks, there will be no hallucinations in it because it just uses a different method. If your math proving automated proving system uses a different method for artificial intelligence that is not based on neural networks, then it will not hallucinate.
Right.
And it's clearly why more models hallucinate when we understand how neural networks actually works in practice. Because they search some sort of optimal, but they can't prove that the optimal is global. So if they're coming from a point where they're reaching a local optimal that doesn't work in a particular situation, that is what people perceive as hallucinations. But it is not a feature of artificial intelligence, it's a feature of neural network, which is the basic of current artificial intelligence.
That's right.
That's the way I see it.
That's right. This is not neural networks. This is just its own functional programming language.
Correct. Yeah, so that's why it will not hallucinate.
That's right. Yeah. Yes.
Well, mathematics is really infamously incomplete, going back to Gödel's incompleteness theory. Do you ever worry about that? Like in the same sense that 100 years ago they tried to axiomatize all of math, found they couldn't. Do you worry that we won't be able to, do that?
Yeah, I do worry about that, but it's like I come back to like this idea of someone was mentioning like, can you reuse these things? And yes, we can create this shared library of truth of just these algebraic relations, and then it's going to set off this self-improving feedback loop where like this AI is at the edge of human knowledge. If you think of all knowledge as a bubble, it's right at the edge. It's got enough context of everything we've ever done, and now with this search strategy that's optimized, it's going to find new knowledge, and we just buckle up and we're ready for the ride because it just gets faster and faster. But you're right though, and I should have mentioned Gödel's incompleteness theorem, and I'm still learning about that. That's a really great point, that all math is still not verified, and that is still a huge issue. But yeah, I always come back to we'll just get the AGI to do it.
Not only not it's verified, cannot be verified.
Cannot be
Even,
verified.
yeah,
doesn't matter how much compute you get, so the math of all, however you specify it, there are some things you cannot prove. So you put 100 million LLMs, you will still not be
Still
able to
not gonna
prove
do
it.
it, yeah. No, that's a huge issue. I gotta learn more about that.
Yeah.
I need to. Yes.
Do you see a potential to use this system to perhaps upload a journal, you know, a peer-reviewed study, and have it sift through it and understand which parts are true and which aren't?
Yeah, and there's existing tools that do that. I wanted to build that first, but I was like, damn it, they already built it. So, but yeah, it's just you upload it. It's like there's a bunch of like SaaS tools I've seen. It's called researchpaper.ai. I saw this one. Yeah, that would be super useful as well, just to do that. Yes.
Why is it preferable to like use proof by deduction rather than like contradiction or like exhaustion? I'm not good at math, sorry.
No, you're right.
Guys, quiet in the back.
No, you're right. It could be done through exhaustion, or I just chose one example here, but you're right. There's so much more to how, like so many more ways we could prove something. Yes.
Is you have like a very well-defined problem here, where it's like you're trying to like solve an optimization problem sort of for like a mathematical function. Do you think all of science can be like abstracted to that, or is like wet lab stuff fundamentally different?
I do think fundamentally we can do it in silico. It's just about like solving physics, like that base. You know, Elon Musk always talks about like looking at the world through like a physics-based first principles view. Physics, like biophysics, like that's a whole field of study. Like how do these molecules and drugs interact? If we can solve physics like the base layer in silico, then we can do all sorts of drug discovery.
Yeah.
I think we can simulate all of reality on a computer. We could be in one right now, so.
So is there no need for like in vivo or stuff?
No need for what?
In vivo experimentation in the future.
We don't have the compute right now.
We don't have the compute right now. Eventually that's the goal. I don't think eventually we will need that, yeah.
Got it, yeah.
It's very archaic, 12 years. I want to see a world where a startup of 3 people can just make a drug discovery startup. You never see that. You need a lot of money.
Mm-hmm.
But if you could do it all in silico and verify it, then you can have people saying like, here's our drugs, and it's like a whole new industry.
Are there any scientific questions that are like so open-ended that like don't fall under this category? Like, I can't even think of one now. But I mean, like life extension, maybe that is actually a very easy thing to optimize for because you're just trying to make people live longer. But are there any like when someone is like beginning a PhD, they don't really know what they're doing and they explore a lot of things. Is that just it's not a well-defined scientific research question then?
I think that there are sciences that are not able to be defined mathematically in this way. A lot more like empirical science, like social science. I haven't thought about it, but I do think that's like, is there an objective beauty? Like I think of it like that kind of question. Like it's. I'm not sure.
Okay.
But I would think there is something outside the scope of this. Yes.
Just building on what you're saying, I mean, how optimistic are you that this generalizes beyond mathematics? I mean, the defining characteristic of mathematics is that it's purely abstract. And even AlphaFold was not proven in the benchmark.
Mm-hmm.
So how optimistic are you that we can use a totally automated discovery pipeline like this realistically in other fields?
I'm pretty optimistic. It's just a question of motivation, I feel. Like the alpha geometry, AlphaFold teams, they collected the right data sets, they put in a lot of time. I feel like this can be done in an open way. Stable diffusion, they have like stable bio as well. There's a bunch of open science projects out there, obviously DeSci, but like, I do think it can be done. It's gonna be difficult, but it can be done. I don't really see any like blocker. Yeah.
Yes, when it will be done and everything will be, really work, what if we will start to use your model for, the 100th century ago proven mathematical stuff, or I don't know. And we will see that people at that time was lying or missing
Many
something.
cases.
Yes, and it's look like with whom we have to trust, with machine or with the people. And it looks like where will be new models for whom we have to really believe. And maybe teachers will teach future children how to connect with the machine and believe, trust in machine, not with our mindset, how we are thinking as human when we solve equals, when we use algebra or whatever. It's so really interesting, and it's like decentralized. What do you think about your future? Where are you going? Because it's changing. It's like already 100 people will talk about it, and it's like booming. Like 1 second. What do you think?
Yeah, I mostly feel excited for the future. You're right, it's moving so fast. You mentioned connecting brains. I do think that's really exciting. There's a great show on this that I just finished watching called Pantheon. It's about uploading your mind to the internet. Yeah, I just feel very excited. I feel like in a lot of ways the golden era hasn't even started. It's about to start in the next 5 to 10 years. And we're going to look back and be like, how could we even live like that before? It's going to be so much better. We're going to have so much more capability when we connect our brains to the machines. And there's like concepts like music that we understand as humans because our brains are smart enough, but like an animal couldn't understand. I feel eventually when we connect our brains to the internet, there will be concepts like music that we'll begin to understand that right now we don't even understand what they are. Similarly in math and science and arts and everything, it's going to be wonderful.
They have BMI meetup groups already.
They have what kind of meetup?
Brain machine based meetup.
Oh, that's very cool. In New York?
And BCI too. Brain computer.
That's awesome. Yes.
I'm not as enthusiastic. The
Yeah.
potential for manipulation is so great. You see what's happening in our last election. The big guys are going to be having control over this technology, and people who are going to connect their brains to the internet, they're going to be controlled by these people.
Well, that's why we got to decentralize the computer, right? Yeah. It could go badly though, yeah. Any other questions?
Thank you guys for coming. Follow Siraj on Twitter. What's your handle?
Siraj Raval, Siraj Rabal.
So make sure to follow him on Twitter. Make sure to follow him on YouTube. He has really great YouTube content. He has really great Twitter content. So make sure to give him a follow. And feel free to ask him questions after. So thank you again. I appreciate it. Have a good night, everybody.
I'm building.
I've seen some pop up on Twitter. Very similar to some of the things that stuff like this. Not often. Oh, just like
Thank you.